In this video, we're going to finish deriving the existence of gravitational waves using a special coordinate system called the Lorenz gauge. We're continuing on from the last video where we wrote the Einstein field equations using linearized gravity, where the metric g equals the flat metric eta plus a small perturbation h, where we used this definition for h with a bar on top. The reason we care about linearized gravity is that gravitational waves can be formulated as vibrations in the metric, which are small deviations away from flat spacetime. The small changes away from flat spacetime are given by the h term in the metric. So, given this equation for the Einstein tensor G in linearized gravity, it's possible to do a change of coordinates where all these terms go to zero except for the last one, which is the D'Alembert of the barred h. This fact basically shows that the metric obeys a wave equation in the vacuum where all the components of the energy-momentum tensor are zero. So under linearized gravity in this coordinate system, the Einstein tensor becomes the D'Alembert of the barred h. And in the vacuum, the energy-momentum tensor goes to zero. So the Einstein field equations become a wave equation for the metric perturbation h bar. The coordinate system where this happens is called the Lorenz gauge, and it greatly simplifies the linearized Einstein field equations. I'll take some time at the end of the video to explain what the term gauge means, but for now you can just think of a gauge as meaning a choice of coordinate system. So in this video we're going to prove that the Lorenz gauge exists and provide a recipe for changing from any coordinate system to the Lorenz gauge coordinate system. And this shows that the Einstein field equations predict that gravitational waves can exist in a vacuum. So we need to prove that there's a coordinate system where these first three terms go to zero. It turns out that if we can find a coordinate system where the partial beta of h bar alpha beta with upper indices equals zero, these first three terms go to zero for free. Remember that raising and lowering indices is done with the metric, so we can feel free to take a term with raised indices, take out the inverse metric, and apply the inverse metric to the lowered indices of another term instead. So basically, we can feel free to take two indices being summed and swap their up and down positions if we want. Let's start with the third term. We can lower the alpha and beta on the derivatives in exchange for raising the alpha and beta on the h bar term. Then, looking at this inner derivative, this is exactly the expression we have for the Lorenz gauge condition. So if we assume the Lorenz gauge condition is true, this goes to zero, meaning the entire third term goes to zero. For this first term, we can lower the alpha on the derivative in exchange for raising the alpha on h bar. We can also raise the nu index to a beta if we add a beta nu metric with lower indices to the expression. This is basically the reverse of lowering an index. Instead of lowering the beta index and eliminating the metric, we're raising the nu index and including the metric. Next, since the order of partial derivatives doesn't matter, and the eta metric is constant, we can move the alpha derivative through so it's sitting next to the h bar term. And since we're always free to relabel indices in a summation, as long as we relabel them consistently, we can relabel alpha as beta and relabel beta as alpha. Finally, since metric components are symmetric, we can switch the alpha and beta indices of the h bar. Once again, inside the brackets, we have the term from the Lorenz gauge condition. If we assume the Lorenz gauge condition is true, this goes to zero and the entire term goes to zero. The second term looks almost exactly like the first term, except some of the indices are relabeled. And we can use the exact same procedure to show that the Lorenz condition causes this term to go to zero as well. So we've shown that if the Lorenz condition is true, and this derivative of h bar with raised indices is zero, the first three terms in this expression for the Einstein tensor all go to zero. So this condition greatly simplifies the Einstein field equations. Now it's our job to prove that there's a coordinate system with this condition that actually exists, and this will be the Lorenz gauge coordinate system. So how do we find a coordinate system where this derivative of h bar is 0? This will involve a coordinate transformation from our old coordinates ct xyz to some new coordinates ct tilde x tilde y tilde z tilde. To summarize this, I can also write the transformation as being from x superscript alpha to x tilde superscript alpha, where the alpha index ranges from 0 to 3. One basic type of coordinate transformation we can use is a displacement field, which means we take all the x alpha coordinates and move them by some small amount psi alpha to get the x tilde alpha coordinates, where the psi denotes the displacement and is different at each space-time point. This means that we take our old coordinates, then displace each coordinate by some small amount, and get the new coordinate system for our space-time. Now we're going to assume these psi displacements are small, so the coordinates never move too far away from their original position. We're also going to assume the derivatives of psi are small, so that there are no drastic changes in the displacement. So to get x tilde, we just take x and add psi. And to do the coordinate transformation in the reverse direction, to get x, we just take x tilde and subtract psi. If we take this first equation and differentiate both sides by x beta, since x alpha and x beta are independent coordinate directions, this partial derivative is always 0, unless alpha and beta are the same index, in which case this goes to 1. So we can rewrite this as an alpha-beta Kronecker delta. We can also take the reverse transformation and differentiate by x tilde beta, setting this to a Kronecker delta as well. And we can use multivariable chain rule to expand this derivative as a summation over x coordinates. So our formula for partial x alpha by partial x tilde beta can be written like this, with the multivariable chain rule expansion, or like this, without the multivariable chain rule expansion. If we change these alpha indices to sigmas, we can plug this in here and distribute. Since we said that the rate of change of psi is small, the product of the two psi derivatives is extremely small and can be ignored. And we can use the Kronecker delta cancellation rule to change this sigma to a beta. So this is our formula for partial x by partial x tilde. Since our aim is to get a metric that satisfies the Lorenz gauge condition, we're going to want to see how the metric tensor components transform under this change of coordinates. So the g tilde metric components are just the dot products of the e tilde basis vectors, which are just the partial derivatives with respect to the x tilde coordinates. We can expand these x tilde derivatives in terms of x derivatives using multivariable chain rule, which gives us the dot products of the x basis vectors, which just gives us the components of the metric in our original coordinate system. We already obtained a formula for partial x over partial x tilde on the previous slide, so we can sub this into these two factors, relabeling the indices as needed. We can also rewrite the g metric as the flat eta metric plus the h perturbation. If we distribute these first two sets of brackets, we get 4 terms. Again, since the derivatives of psi are small, the product of psi derivatives is very small, so we ignore it. I'm also going to rewrite these psi derivatives using comma notation, where the derivative with respect to x beta is denoted by a comma beta subscript, and the derivative with respect to x alpha is denoted by comma alpha. Next, we distribute these 3 terms over these 2 terms to get 6 terms. I've also used the Kronecker deltas to relabel some of the mu's to alphas and relabel some of the nu's to betas. Next, since the h components are small and the psi derivatives are small, their product is small enough to be ignored. Finally, I'll combine eta and h into g, and use these extra metrics to lower the nu to an alpha, and lower this mu to a beta. So this is how the metric transforms when we do a change of coordinates involving a displacement field psi. If we take both metrics to be the flat eta metric plus a small perturbation h, we can cancel the etas and see that the h perturbations transform in the exact same way as g. As an aside, we can use the change of coordinates formula for the components of h to determine a change of coordinates formula for the components of the Riemann curvature tensor in linearized gravity. If I rewrite these four terms in a column, I can replace all the h tildes with the transformation formulas. Then I can distribute the partial derivatives and turn them into comma subscripts on the xi's. Now, we need to be careful with our derivative notation because these derivatives are in the tilde coordinates and these derivatives are in the original coordinates. But this turns out not to matter. If we expand partial xi by partial x tilde using multivariable chain rule, then sub in our formula for partial x by partial x tilde, this product of small derivatives goes to 0. So because xi derivatives are small, partial xi by partial x tilde is the same as partial xi by partial x. And the same can be said for derivatives of h since those are small as well. Since the order of partial derivatives doesn't matter, the order of the indices after the commas also don't matter. And all the xi terms cancel each other in pairs, leaving only the h terms, which just gives us the Riemann tensor components in the original coordinates. So what this means is the Riemann tensor components don't change under a change of coordinates from a small displacement field psi. So our goal is to change coordinates so that our new value of h tilde bar satisfies this Lorenz condition. Remember, the h bar is defined as h minus 1/2 eta times the trace of h. This applies in the tilde coordinates as well. Since it can be hard to read both the tilde and the bar above the h, from now on I'm going to make the bar above h bar longer so that it's easier to read. So we know how h transforms under a displacement field, and we have our definition for h tilde bar, where we can write the trace of h tilde using h tilde and an inverse eta. We can plug in h tilde from our transformation formula into the h tilde bar definition. We can then distribute 1/2 and these etas over these three terms. Eta inverse summed with the h components gives us the trace of h. And we can use these inverse etas to raise the alpha and beta indices on these xi's. We can then write this combination of terms as h bar, and combine these two 1/2s into a single term. This formula tells us how our h bar components transform under a change of coordinates using a displacement field psi. And if we sum on both sides with two inverse etas, we can get a similar transformation formula for h bar with raised indices. Some of these etas can raise mu and nu indices, and if we take the derivative of all terms in the beta direction, because the order of partial derivatives doesn't matter, and because the eta metric is symmetric, these last two terms are actually equal if we relabel the summation indices in the right way. So they cancel out. And if we change from comma notation to partial derivative notation, this just becomes the square D'Alembert operator. So if we're in a coordinate system with a given h bar, and we choose a displacement field psi that has this property, that this partial summed with the raised h bar components is equal to the D'Alembert of psi, this would mean that the right-hand side of the above equation goes to 0, meaning that the new tilde coordinate system satisfies the condition for the Lorenz gauge coordinate system. So this basically gives us instructions for changing to a coordinate system that meets the Lorenz gauge condition. We know how h bar transforms under a displacement field psi, And if we specifically choose our displacement field psi to satisfy this differential equation, the new coordinate system we will end up with will meet the Lorenz gauge condition. Now, it's important to notice that the choice of displacement field psi for getting the Lorenz gauge is not unique. For example, a second displacement field chi that has the property of having a zero D'Alembertian can be added to psi. And since its D'Alembertian goes to zero, this differential equation is still satisfied. So the displacement field xi plus chi will also bring us to a Lorenz gauge coordinate system. So the Lorenz gauge is really a class of coordinate systems, not just a single coordinate system, since there are multiple different coordinate systems that satisfy the Lorenz gauge condition. And recall, in any Lorenz gauge coordinate system, these first three terms in the formula for the Einstein tensor go to zero. So we're left with the Einstein tensor equaling -1/2 of the D'Alembertian of h bar. And if we're in a vacuum where the energy momentum tensor is zero, this directly shows us that the metric perturbation h bar is a solution to the wave equation. So in Lorenz gauge coordinates in the vacuum, the h bar components satisfy the wave equation, written here using the square D'Alembertian operator. We can also rewrite the D'Alembertian as second derivatives of our spacetime coordinates, and rewrite the spatial derivatives as the Laplacian operator. This gives us the more familiar wave equation from non-relativistic physics. Therefore, the Einstein field equations predict the existence of waves that can travel through the curvature of spacetime in the form of small perturbations away from the flat metric. And we can see here that the gravitational waves travel through spacetime at the speed of light c. So this implies that the effects of gravity are not instantaneous like in Newtonian gravity. Instead, gravity travels at the speed of light c, which is basically like the maximum speed of cause and effect in spacetime. And just to be clear, these gravitational waves exist in all coordinate systems. Coordinate systems are a human invention, and they have absolutely no impact on the real physics that actually takes place. It's just that the Lorenz gauge coordinate system gives us an equation where the existence of gravitational waves becomes very clear and obvious. In the next video, we're going to look at another coordinate system called the transverse traceless gauge. And this will help us see that gravitational waves have two polarizations called the plus and cross polarizations. To finish this video, I'm also going to take a few minutes to talk about the Lorenz gauge in electricity and magnetism, and how it relates to the Lorenz gauge in general relativity. If I make a video on relativistic electricity and magnetism, I'll link it in the description, but for now I'll just give a quick review. Loosely speaking, a gauge is sort of like a choice that we have the freedom to make. And this choice does not result in any changes in our physical system. When it comes to electrostatics, where no electric charges are moving, the electric force on a charge is equal to the charge Q times the electric field E at a given point. The electric field E can also be expressed as the negative gradient of the electric potential phi. This basically means the positive charge will roll down to the lowest potential. An important fact is that different potentials can result in the same electric field and the same physics. If I take a potential phi and add a constant k to it, since the gradient of a constant is zero, phi plus k results in the same electric field as phi. So the transformation of adding a constant potential leaves the electric field unchanged. A magnetic field B can always be expressed as the curl of the magnetic vector potential A. Again, there are multiple vector potentials that can result in the same magnetic field. If we have a vector potential A and add the gradient of a function to it, this will result in the same magnetic field, since the curl of a gradient is zero. So the transformation of adding a gradient of a function to the magnetic vector potential leaves the magnetic field unchanged. If we upgrade to electrodynamics with moving charges, The electric field is now the negative gradient of phi minus the time derivative of A. These two equations each give three formulas for the XYZ components of the E and B fields. Now, it's possible to take the scalar electric potential and the 3D magnetic vector potential and combine them into a 4-vector potential, curly A. This is how we write potentials in special relativity. We can also write a 4 covector potential as a row, with the components lowered with the metric. We can then rewrite these 6 equations using the 4 potential, if we include some factors of C. You'll notice that each of these 6 formulas depend on a unique pair of spacetime coordinates. And we will define these as the components of a rank 2 tensor F called the Faraday tensor, where the mu nu entry equals this formula. The Faraday tensor unites the electric and magnetic fields into a single tensor that is obtained from the 4 potential curly A. Just as before, different 4 potentials can result in the same Faraday tensor, and the same physics. If we take a vector potential and add the derivative of a function f, the result is the same Faraday tensor as the original vector potential. There are multiple possible 4 potentials that will create the same Faraday tensor, so we have some amount of freedom in picking our 4 potential. This freedom to pick a potential is called a gauge freedom, and choosing a specific potential is called choosing a gauge. Changing from one potential to another in such a way that we don't change the components of the Faraday tensor is called a gauge transformation. So we have freedom in choosing our potential. The specific choice of potential that obeys this formula, where the 4 divergence of the potential is 0, is called the Lorenz gauge. The Lorenz gauge is named after Ludwig Lorenz, who should not be confused with Hendrik Lorentz, after whom the Lorentz transform and Lorentz force are named after. This whole process in electricity and magnetism is analogous to what we talked about in this video in linearized general relativity. In E&M, we have the freedom to pick the 4 potential A, and in linearized GR, we have the freedom to choose spacetime coordinates, and those coordinates come with a specific metric perturbation h. In E&M, multiple different 4 potentials can give us the same Faraday tensor components. And in linearized GR, multiple metric perturbations can give us the same Riemann tensor components. In E&M, a gauge transformation is a change in the 4 potential that doesn't change the Faraday tensor components, and looks like this. In linearized GR, the gauge transformation is a coordinate displacement field that doesn't change the components of the Riemann tensor. Finally, in E&M, the Lorenz gauge is a choice of 4 potential that obeys this 0-4 divergence condition. And in linearized GR, the Lorenz gauge is a choice of coordinates that causes the metric perturbation h to obey this 0-4 divergence equation. So given any choice of coordinates in linearized gravity, we always have the ability to choose a displacement field psi, which is a gauge transformation, to bring us to the Lorenz gauge, which is a coordinate system that obeys this property. And this gauge transformation will not change the components of the Riemann tensor. And that's all I plan to say about gauges for now.